More on NPV and internal rate of return. So we will cover here what happens with the NPV and the internal rate of return when we have irregular cash flows, and I'll explain what I mean by irregular cash flow in a second. So we will say, for the sake of this course, so life can be completely different, but for the sake of this course, we will say a project with irregular cash flows will be as follows. So we pay upfront. So there are startup costs. The project generates positive cash flows in the middle, and at the end completely we have to clean up the mess, okay, and dismantle. So there's a second set of negative cash flows at the end. So pay first, receive in the middle, pay at the end. So this is what we mean by irregular cash flows. Here's an example. So how is it different from what we just did? So we have an initial investment I0 at time 0, 5 cash flows C1, C2, C3, C4, C5 at time 1, 2, 3, 4, 5. And there's a cleanup cost represented by Z, which value is calculated as of time 5. So the net present value is, so we have an investment first and a cost at the end completely, and positive cash flows in the middle. Good. So when the interest rate is equal to 0, what is the net present value of the project? So the sum of all cash flows, including the subtraction of Z. When the interest rate goes to infinity, it's simply the minus the investment. So the graph of the net present value of a project with irregular cash flows will most often look like this. So if Z is sufficiently large that the net present value at time 0 is negative, the graph will look like this. So initially negative net present value, but then as R increases, as R increases, the value of Z decreases and NPV becomes positive, but it eventually falls back towards the initial investment. So the limit when R goes to infinity hasn't changed. The only thing that has changed is what happens when the interest rate is equal to 0. If the sum of all cash flows is greater than 0, then the graph of the net present value of a project with cleanup costs will look like this. Here's an example, and that's the example you see in the problems I gave you for the quiz. So there's an initial investment that made at time 0, 5 cash flows at time 1, 2, 3, 4, 5, and then there's going to be an annual cleanup costs to be paid forever beginning at time 6. So from time 6 and on, the company has to pay K just to maintain the field, to clean up, to rearrange whatever the space it used. So assume for now that K will be paid forever. I mean, if K is paid forever, it's a constant amount, it's a perpetuity starting at time 6. Well, the present value of all the K's to be paid from time 6 and after, as of time 5, is K divided by R. So that's the present value of a constant perpetuity. Which means if we could replace here in our setup Z by K divided by R. So what we subtract from C5 at time 5 is the present value of the perpetuity K is equal to the perpetuity paying K annually every year forever starting at time 6. So the net present value is given by this equation here. So I have replaced Z by K divided by R. What happens when the net what happens to the net present value of this project when the interest rate is equal to 0? Well, we have the initial investment as before, the sum of all cash flows as before, but then the present value of the perpetuity when the interest rate is equal to 0 is infinite. So at the end, completely with a rate of 0, we subtract infinity from the net present value. So the net present value when the interest rate is equal to 0 in this case is minus infinity. So on the graph of the net present value here, as the interest rate approaches 0, the net present value drops to infinity. Now suppose we are less severe, okay, and instead of having cleanup costs that are constant forever, so they could just decrease over time. So we need to clean up the field, but I mean the cost of cleaning up will eventually fade away. So cleaning costs decrease annually at the rate D. So it's like they grow annually at a growth rate minus D. So K1 is 1 minus D times K. K2 is 1 minus D squared times K. So here the present value sitting at time 5, the present value of this negatively growing perpetuity beginning at time 6 with payment minus K is minus K divided by R minus the growth rate. So the growth rate is minus D. So it's the depreciation rate. So it's minus K divided by R plus D. So in this case, when R goes to 0, this the value of this term here does not go to minus infinity. So it remains finite. It can be extremely small. So if K is 100 and D is 0.001, the value of this term here will be very, very negative. It's going to be like a big negative number. But it won't be minus infinity, and it could be small enough to make sure we have a positive net present value when the interest rate is equal to 0. Okay, so in this case here, the NPV does not go to minus infinity when the interest rate is equal to 0, but it will be negative when D is sufficiently small. So that would be the more the more general model, the most general model of project with irregular cash flows we will see in this class. So see, and what is the limit when the interest rate goes to infinity? So so it's simply minus the initial investment, regardless of what happens with the cleanup cost. So the graph of the NPV of a project with irregular cash flows will always have this shape here. What does this mean? First, so we have negative NPV when the interest rate is small, negative NPV when the interest rate is large. So there has to be a region, an interval of interest rates at which the net present value is positive. Otherwise, the project would just be a money-losing adventure, and there's no reason here to deal with money-losing projects. So in the case of projects with irregular cash flows, there will always be like a region. So when the questions are about internal rates of return or other concepts, there will most of the time be a region where the net present value of the project will be positive. So what happens with these projects? They have two internal rates of return. So there is one first internal rate of return where the NPV is equal to 0 when the NPV goes from negative to positive. So when the net present value enters positive territory, it crosses the first internal rate of return. Then it's positive for a while and it starts falling towards minus I0. and at some point in time it will cross the horizontal axis at the point that is the second, that corresponds to the second internal rate of return of the project. And there's going to be a region between the two internal rates of return where the NPV will be positive. If the project is such that the sum of all cash flows when the interest rate is equal to 0 is positive, then this project has a unique internal rate of return, just like regular projects. It's only when the net present value of the project at R is equal to 0 is negative, then the project will have two internal rates of return. So we summarize this result here. So if the project with irregular cash flow is such that its NPV is positive when the interest rate is 0, then this project has a unique internal rate of return. But if the NPV when the interest rate is equal to 0 is negative, then the project will have two internal rates of return, okay, assuming that there are rates of return at which the net present value is positive. And here's an example of questions I may ask with respect to internal rates of return of projects with irregular cash flows. So we have a project with an initial that require an initial investment of $282 at time 0 and promises a cash inflow of $47 at the end of the next 14 years. After year 14, dismantling the installation and cleaning up the field will cost the firm $11 per year forever. At what range? In what interval of discount rates is the NPV of this project positive? So, and then you have like 4 intervals. So note that some of these intervals have only positive values, and there are answers where it suggests that the NPV could be positive between 0 and something. So the answers specifying that the NPV could be positive for discount rates between 0 and something, they refer to situations where the project would have a unique internal rate of return. When you have an interval including two positive rates of return, so this refers to situations where the project would have two internal rates of return. How do we solve this question? So here's the mechanic you should be using to answer these questions. So step 1, compute the NPV when the interest rate is equal to 0. That is, compute the sum of all cash flows of this project. If the NPV is greater than 0, go to step 2A. If the NPV is smaller than 0, go to step 2B. If the NPV is greater than 0, the project has a unique IRR, which means that the correct solution takes the form the NPV of this project is only positive for discount rates between 0 and something, where you have to verify that the second rate mentioned gives an NPV close to 0 or closer to 0 than all the other solutions, starting with suggesting an interval from 0 to whatever. If the NPV computed with an interest rate of 0 is negative, then the project has two internal rates of return, in which case the NPV has to be computed with the two rates proposed in the correct solution, and there's a way to find the best answer among the choices proposed, and I'll show you in a minute. So the project requires an initial investment of $282. That the payoff to the project is $47 per year for 14 years. At the end of everything, there will be cleanup costs incurred forever, and these cleanup costs are $11 per year forever. So whenever there's no depreciation in the cleanup cost, the last term includes a term costs divided by R, So for sure, when r goes to 0, this goes to minus infinity. So what is the NPV of this project when the interest rate is equal to 0? It's minus the infinity. But whenever you have constant cleanup costs forever, you know that you have a case with two internal rates of return. Then we have two internal rates of return. So we go to step 2B. So we need to try to look at what happens, okay, to the NPV of the project around the interest rates proposed here. So of all the proposed answers, the best answer is the NPV of this project is positive for discount rates between 3 and 12. Okay, why? Because at these rates, if these are the correct internal rates of return, there should be a change in the sign of the net present value around these rates. So if the NPV is positive for rates between 3 and 12.9, this means that below 3, the NPV is negative, and above 12.9, the NPV is also negative. So here we have computed the net present value of the project when the interest rate was 2.9%, so 0.1% below 3%. And that gave us a net present value of minus 1.65. And then we compare this net present value to the net present value when the interest rate is 3. Okay, so nothing has changed here except the interest rate. And this gives us a net present value of 6.6. So from 2.9 to 3, the sign of the net present value goes from negative to positive. So around 3%, there is an internal rate of return. Now we need to verify that 12.9 is also approximately an internal rate of return. So from 12.9 to past 12.9, the net present value should go to positive, from positive to negative. So net present value at 12.9 is 0.09. Net present value at 13, so 12.9 plus 0.1 is negative. So the best answer is this one. So around 3% and close to 12.9%, the project has an internal rate of return. So these are approximately the discount rates at which the net present value of the project is equal to 0. So best answer here is B. So A does not work because you don't have NPVs close to 0, around 14.9 and 51.7. It's not positive at 0, so the answer cannot be C. And the last answer, D, is incorrect because at 48.4, net present value is negative, and 12.1, although it's not too far from an internal rate of return. I mean, it's so that, I mean, the NPV is negative for a whole bunch of discount rates between 12.1 and 48.4.